Hello, this is Mr. Yeager, continuing on with the projectiles section. Um, Again, what we have just learned from the prior video was basically all the details about projectile motion. Very specifically, the idea is that we have to separate out the x and y components of all vector quantities of displacement, velocity, and acceleration. But in doing so, we also learn that there is zero acceleration in the x direction, in the horizontal direction, which means the horizontal velocity is constant, but the vertical velocity is accelerated due to the acceleration of gravity. All right. So basically, from there now, there's two major situations for projectiles. One is called the zero launch. The other one is called the angled launch, which will be a separate video unto itself. So we are going to first look at the zero launch because it helps at least. It makes the problem just ever so slightly more simple than an angled launch. Angled launch only adds one extra step to the problem at the beginning, but we like to start with zero launch because it is seen as slightly easier than an angled launch problem. Okay, so what we're looking at is, when I say a zero launch, I'm talking about the launch angle, the angle at which the projectile is released. All right, and this is almost always related to the horizontal. So we're going to basically we have to imagine a horizontal plane, and the angle is either going to be above that horizontal plane or below that horizontal plane. Okay, is what we're looking at. That would be my launch angle. So again, this will determine what type of trajectory I have. Obviously, all trajectories will turn into a parabola, but it'll show me like, okay, is it going to be a full curve parabola, or am I only going to see basically one half side of the parabola? All right. These launch angles will always be between 0 and 90 degrees above horizontal. Now, I will say you could technically have somebody that is already on a building, and you're going to shoot below the horizontal or throw below the horizontal. So it'll be 0 to 90 above or below. We don't do anything with negative degrees at all. We're not going to say that. The problem will specifically say 30 degrees above the horizontal, 30 degrees below the horizontal. Okay. So again, this goes back to the picture you've already seen. This is an example of a 0-degree launch where you have your cannon. It's completely flat. There is no angle basically with the horizontal. It's trying to shoot that cannonball directly horizontal off of this particular cliff. When we do zero launch, we're obviously always going to be above ground, because if you do a zero launch on a flat surface, it's just going to roll across the floor, and that's not 2D motion. We want to add in the effect of gravity on it, and again, this is trying to show you that if there was no gravity, the white spheres would obviously represent the direction the cannonball would like to go at a constant speed, but with gravity, we get the red spheres, and they are the one that is the obviously parabolic trajectory we will get. Okay? Now, because it's a perfect 0-degree launch, this will help, again, simplify part of the problem a little bit. All right, we got to be able to recognize this well. All right, so again, you have that perfect initial velocity that's perfectly horizontal. I'll go ahead and say it already. What basically happens is there is no Vy component. Okay, and so what we're going to say is V naught y equals 0. There is no initial y velocity. So this initial velocity that's being released, this is technically a resultant velocity. It is entirely a horizontal velocity. So basically what's happening here is, instead of having to figure out x and y, I'm giving you x, and technically I'm giving you y by saying it's 0. From there, we will go ahead and then solve the rest of the problem. All right. So when you launch something perfectly horizontally, it'll follow this parabolic path. All right. You are going to be given that velocity. If it says 0 launched horizontally, is your horizontal velocity. And what do we know about the horizontal velocity? It does not change. So you're given that for the whole problem. We're going to try to find the horizontal range. Okay, we don't have to say horizontal range means horizontal, but just to make sure that we're really clear about it. Obviously, the distance that the sphere travels, the cannonball travels from its initial platform. You will be given an initial height, because you got to be above ground. Again, if you're on the ground, that object's just going to roll across the floor, and that's not what we're looking for. All right. We're going to try to find the total time in air. That'll be one of the key things. How long will this object stay in the air for? All right. So some major things to remember. All right. There is no horizontal acceleration, so your horizontal velocity stays the same the entire time. There is no initial vertical velocity. So again, we're already giving you some of these numbers. Go back, think about that prior video on just general projectile motion. We already are given some of these values, and it's a kinematic problem. As long as you have 3 out of the 5 values, you're good to go, and 0 counts as one of the values. The horizontal velocity will stay constant. That kind of refers back to the first point. Okay? And the time is the same for both vertical and horizontal. Time is a scalar quantity, therefore it's not affected horizontally or vertically. All right? So really, there's only 2 equations that really are important in this. It's our range equation, which again we saw in our previous video. All right? This is the only equation for the horizontal motion. There isn't anyone. As we showed, all the other kinematic formulas just tell us that initial and final velocity are the same. The vertical velocity will equal 1/2 gt squared. Where does this come from? It is, I'll change colors here. Delta y equals v naught y t plus 1/2. Again, I'll put in a y t squared. V naught y is 0, so this whole thing goes away. So delta y equals 1/2 ay is gt squared. That's where they get the 0.5. All right. So again, that goes way back all the way to basically free fall, where we talked. Actually, no, early kinematics, where we said, hey, if you have no initial velocity, get rid of that first part of this this equation, the delta y v naught y t plus 1/2 at squared equation. So these are going to be your 2 main points. I'm going to say this probably many times during this video and during probably the next video. The vertical tells you how long you're in the air. Okay? A common error is people go, I don't know where to start again. I mean, that's the common complaint. I don't know where to start. I don't get it. Where do I go? How do I figure out time? Why shouldn't I use the horizontal? Because that has time in it. Okay? Obviously, you can solve for time with the horizontal equation, but I have to then give you dx and vx, and that is very rare. Okay? That's not a common thing that's given to you in the problem. The vertical tells you how long it's in the air, because even if you go back and think about the prior slide, I'll go ahead and go back to the prior slide real fast. Okay? Maybe. All right. If there was no gravity, the horizontal component will never, you'll never land. So again, gravity, how strong gravity is, tells you how quickly that object will come to the ground, tells you how long it'll take to come to the ground. Okay? So that is very important. Okay? You usually start with this y equation. All right. Right here, again, if you get to, this is obviously, if you're able to go look at some of these extra videos I have, this again is trying to show you really clearly what's happening with the vertical and horizontal velocities as a projectile flies through the air. All right. And this is an excellent, if you can't find it, look up Mythbusters and basically watch the end of the episode where they try to determine, that they try to do the myth of, will a drop bullet hit the ground faster than a fired bullet, a perfectly horizontally fired bullet? The answer is both of these will hit the ground at the same time. All right? This is a classic, it turns out, hey, yes, this is true. They both will hit the ground at the same time. Let me finish that, at the same time. And that's because, obviously, a lot of people sit there and go, nah, I think the bullet drop's going to hit the ground faster because it doesn't go as far. Okay, you're correct in the second part. It won't go as far. If you drop it, it's not really going anywhere, all right, other than straight down. But think about it. Think about what I just said. What equation will tell you how quickly something comes to the ground? It's the y equation. If both of these start at the same delta y, it would be 1/2 gt squared for both of them. All right, is either one going to be affected by gravity any differently? The answer is no. Obviously, in the Mythbusters episode, you have that wind resistance factor, all right, So it doesn't come out exactly the same, but it comes out basically within like the level of error that you're expecting, essentially saying that they both do hit the ground at the same time. At least that you cannot see it. Okay, there's no way you're going to be able to see unless you slow it down to such a degree to be able to see the difference between the two. But basically the idea is, again, this goes back to when we talked about free fall, everything hits the ground at the same time. So it's due to all masses accelerated by gravity the same. Okay? And so it doesn't matter. As long as you shoot it horizontally, all right? The faster, again, you can see in this, do you see the horizontal velocity in this equation? The answer is no. So even if I fire something twice as fast as the first one, which one's going to hit the ground first? The answer is they'll hit the ground at the same time. One will travel farther. That's definitely true because the distance that it travels, the range that it travels, is related to Vx. But they are both at the same height. This is a classic AP question. This is a classic regular physics question. All right. All the stuff that we've talked about in terms of doubling and tripling, if I half the height, what happens to time? Be prepared for that. Be prepared to think about, okay, if I double the height, how much longer will it take to hit the ground? Well, it's going to be √2 because, again, t is squared, so I need to make sure I put a 2 in front of it. Delta y is related to t squared. If I put a 2 here, I have to square the square root of 2 to get a 2 in front of 2t squared. Okay? So I know I'm going a little bit all over the place right now, just thinking of a couple different things. But this is a very, very good, important point to realize that everything hits the ground at the same time. Okay? It only depends on the height. All right? So practice problem. So this is basically it. Let's go through this. So a marble rolls on a table with a velocity of 5 meters per second. The marble rolls off the table, which is 1.5 meters high. Okay? These are usually the questions you'll get. All right? On a test, obviously I'm only maybe asking for one at a time. I'll ask one and then maybe in a different problem ask for a different one. But these are the main things we're interested in finding. How long will it take in the air? How far will it go? And what would be the velocity when it hits the ground? That's the only one that I've talked about back in the prior video where we actually do have to recombine the components. A and B, we want to keep it separate components. So here we go. So for A, how long would it take to hit the ground? All right, again, you need 3 out of 5 components to be at 3 out of 5 variables in either the x or the y to solve for these problems. Okay? So this is what you know. You know the velocity. This is the velocity that it rolls on the table. It doesn't tell you that's the x velocity, but it's moving horizontally, so guess what? That's a 0-degree launch. That means the v is equal to the vx, and v naught y or viy is equal to 0 because the marble is not moving up or down prior to leaving the table. Okay? So what else do we know? We know y is 1.5 meters, that's the height, and g is 9.8 meters per second squared because that would be your ay. Again, you can use 10. I know I have 9.8 a lot in here. You can use 10. Okay? So this would be your ay. So look at that. You know 3 variables, viy, y, and g. You can solve now anything in the y direction. And again, the y equation is what you use to find time. Okay? You got to use that. All right? Even though it's probably on the next page, delta x equals vxt. A lot of people want to go to this because they go, I know what vx is, but you don't know what either other of these variables are. You do not. So, and that's the only equation in the x direction, so that one is worthless. We have to go to the y equations. All right? So here we go, solving for time. Again, these are your 2 main equations. The first one won't work because you don't know, because you only know Vx. The second one, though, we do have 3 out of the 5 variables. Now, let me quickly say this. Some people go, well, can't I try this one? Because isn't the final velocity in the y direction 0 because it hits the ground? No. No, 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 no. Again, when we look at these problems, we're going to look at it all the way up to just at the moment it hits the ground. So it still has a velocity as it hits the ground. So this equation will not work to figure out time. So be careful there. The final y velocity is not equal to 0. Okay. So I'm going to use the second equation. And you can see I just plug everything on in. 1.5 equals 0t plus 1 half 9.8 t squared. 1.5 equals 4.9 t squared. T equals 0.55 seconds. Now real quick, obviously some people go, wait a minute, I thought g is supposed to be negative. Well, the thing is, guys, this is my little trick with this. Which way is this object going vertically the entire time? The only direction that this goes is down. So I'm going to make down positive. So anything that points down is a positive change. It's a positive vector quantity. All right? What we have to recognize is you start at 1.5 and end at 0. So technically, the change in height is negative 1.5. But if I say down is positive, this becomes positive 1.5 change. Okay? So that's a little tricky for people to realize, because a lot of people, what will happen, and usually they can make the adjustment, they realize what they do, is a lot of people go, I thought g is negative, I have to make it negative. I've never said g is negative. I said g is down. G is directionally down. You decide what is positive, what direction is positive and negative. All right? What will happen, though, is if you happen to make this negative, almost all my students will always make this positive. They won't think that it should be negative if I make g negative. Obviously, you'll come out to a negative square root. Most people then figure out, well, maybe I get rid of the negative sign and I can get 0.55. All right? So be careful there. In these zero launch problems, I'm going to say down is positive. So I keep all my numbers positive, which is nice. Okay? So this object stays in the air for 0.55 seconds. This is how we solve all times when an object flies off horizontally. All right? What about the range? This is always the easier part. There's only one formula for solving the range, dx equals vxt. Now that you know, we already know that the velocity is 5. That's the initial x velocity, which is the final x velocity. We now know that it's in the air for 0.55 seconds. I can multiply these two. This object will go to 2.75 meters, okay, in 0.55 seconds. All right? What about the last one? All right, this is always the one where people sit there and go, I just don't get it, okay? I get a lot of people that kind of accept A and B very well. C is the only one that even a very good student sits there and goes, I still don't understand how you're doing this. Okay, so pay attention to this. How will the object hit the ground? Okay, we're asking what is the velocity when the object hits the ground? The thing is, when the object hits the ground, it's going to hit at an angle. Okay, again, velocity is tangent to the trajectory. Okay, tangent to the curved trajectory, the parabolic trajectory. All right. The question is, what is the velocity? Not what is the x velocity or what is the vertical velocity. Okay. Not one of those. What is the overall velocity just as it hits the ground? And again, the answer is not 0. It's just as it hits the ground. So it'll hit at an angle, which means you need to find Vx and Vy. The thing is, you know what Vx is, and a lot of people get this. They know Vx stays the same. So I have this, basically I'll draw that out here. I'm trying to solve a V. We know the x component. The x component in this problem is 5 meters per second because it does not change. What people struggle with is going, how do I figure out the y? I don't understand. How do I figure out the y? Well, it's being accelerated due to gravity. Well, the thing is, guys, you now have 4 out of the 5 variables. You have the initial y velocity, you have the height, you have the acceleration, and now you also have the time. So you have all of the information you need to solve this. Okay? And so what the equation I usually go to would be the Vfy equals V naught y plus gt. This would be the equation I'd recommend going to. Again, hopefully you have your time right. Okay, obviously it does depend that you get the time right. But if you use this equation, this is an easy equation. We actually used this sum back when we did free fall problems. 0 plus 9.8 times 0.55. Remember, if I drop something, there is, which basically that's what's happening here. Okay, there is no initial throw to the ground. It's only rolling off. The y velocity is 0, so Vfy is just equal to gt. Now, this is not the final answer. Sometimes again, I'm trying to warn you of all the mistakes that I see students have done over all these years. A lot of people will say, final answer 5.4 meters per second. I'm like, you're so close. You're so close. All right, that's the VFY. So you have one last thing to do. You have to do some vector, obviously, addition. Okay? You now know that the horizontal is 5, the vertical is 5.4. What would the hypotenuse be? So you have to just put it all together with Pythagorean theorem, and your answer comes out to 7.36 meters per second. Okay? So that is basically it. I don't think I have anything on the next page. Oh, yeah, you're going to just practice. So main ideas is that, again, the vertical equation tells you how much time it takes to hit the ground. The vertical equation is almost always the way to do it, unless I just happen to give you the range and the the x velocity. Obviously, anything that comes off horizontally, you know the x velocity. You don't have to change it in the components. You know the x velocity, and it doesn't change the whole time. After you find the time, just plug it into the range formula, and then when we do the when you're trying to find the final velocity, okay, again, you have the x, find the y, doing g times t, and then plug it into a triangle, the Pythagorean theorem, to solve for the hypotenuse. All right, thank you.